All right, so just a couple of reminders. You have a homework assignment over the interparticle forces that we talked about on Monday, and that is due tomorrow night. And then you were supposed to have read the end of chapter 8 for today. We're going to talk about molecular orbital theory. Some of you have still not completed vocab 10. I have about 2/3 of you have turned that in, maybe a little bit more. So that means a good 15 between my two classes probably have not. So make sure that you get that turned in. You lose a little bit of credit for being late. And then I've created a new homework assignment based on what we're going to be talking about today. And so what I'm hoping to do is to kind of go through how we work with molecular orbitals and then give you an opportunity to work with each other on some example problems. Let's see. Yeah, I think that covers everything. Okay. The first thing that I want to do is I want to look at reviewing the interparticle forces a little bit, just going through some examples of identifying what are the interparticle forces in a given compound. All right, so if you have your flow chart with you, go ahead and pull that out so that you can kind of go through and ask yourselves the various questions for each of those to determine which is the dominant interparticle force. Now, do remember that for hydrogen bonding, the hydrogen has to be attached to oxygen, nitrogen, or fluorine, okay? If necessary, you might want to sketch out the dot structure to see if the dot structure makes it look like it's polar. All right, so I'm going to pause you just for a second to look at this first one. Anybody know the name of this chemical here? CH3OH? Close. So we have to think of what's the prefix for only one carbon. Methanol. Very good. Okay, so this is methanol. And so what did we come up with? Hydrogen bonding. And I would agree with that because we've got this OH bond here. So the dominant force here is hydrogen bonding. Now on your homework, you'll notice that sometimes it'll say, what kinds of forces do these two chemicals have in common? So then we need to pay attention to what are some of the other forces. So we always know that every molecule has what force? London dispersion, that's our weakest. And sometimes it'll just list it as dispersion. You won't necessarily see London. Is it an ionic? No, because there's no metal. Is it polar? Yes. So we have a central atom with no lone pairs, but we have different atoms. So there's an oxygen and 3 hydrogens attached. So if they're not the same atoms on there and they're not directly across from one another, then we have a mismatch that's going to create a polarity. So this is also a dipole. But if we're asked what's the dominant force is the strongest, which is the hydrogen bond. Okay. Let's look at the SF4. How many people think this is ion-ion? Hydrogen bonding? Dipole-dipole? London dispersion. Okay. So this is one where it's a good idea to draw it out. We have 6 electrons for sulfur, 7 for each of the fluorines. There are 4 of them, so 7 times 4 is going to be 28, plus 6 will give me 34 electrons. So when I draw this, I'm going to have a lone pair of my central atom. So what does that tell me? That is polar. Okay, so if you have something that it could either be polar or London dispersion forces, then it's a good idea to draw out the structure to see if there's lone pairs there. All right, what about CH3F? How many people think that's ion-ion? Hydrogen bonding. Dipole-dipole. Okay, dispersion. Okay, so most of you just are either too lazy or too chicken to raise your hand. So on, be brave. So I was put this one here just to remind you that if this hydrogen is not attached to the fluorine, then it's not hydrogen bonding. So this is the dipole. The few of you that raised your hands did do that. So since there is no hydrogen attached here, these hydrogens share their electrons pretty equally, and so they don't carry as much of a positive charge, and because of that, there's not as strong of an attraction. And so we would say this is dipole-dipole. And of course, it also has London dispersion forces, but the dominant force is the dipole-dipole. All right, let's look at CH3NH3. Ion-ion. Good. Hydrogen bonding? Yes, so often hydrogen bonding involves oxygen, but it can also involve nitrogen or fluorine. So whenever we see, this is called an amine group, this is methylamine, so methyl for the C group there, and amine is for the second one. When we have an NH2 group on anything, it's called an amine, and that one has hydrogen bond. It is also polar, and it also has dispersion forces. This one was good. All right, so our last one is the calcium sulfate. How many people think this is ion-ion? All right, hydrogen bonding, dipole-dipole, dispersion. All right, half of you aren't raising your hands here, so you're not making any guesses. The more you engage in these kinds of questionings, the better you're going to learn it, because you're going to either get the feedback that my guess was correct, and then your brain releases endorphins saying, hooray, or you're going to get the feedback that you were incorrect, and then you're going to get a message from your brain that, oh, I need to figure out how to get those endorphins, because those are fun. So yeah, this one is ion-ion. Calcium is a metal. And then we've got nonmetals over there. So that is an ion-ion interaction. Okay. And we are going to look at molecular orbital theory. So we have looked at several theories or models of how to explain bonding. All right, and so sometimes it's just a matter of explaining why we have the certain number of attachments that we have. Sometimes it helps us predict the shape. That would be Vesper theory. And sometimes it helps us to understand how the atomic orbitals can make those kinds of bonds. So valence bond theory does that. Each of these has their limitations. And so that's something that we always say about models. They're the lies we tell ourselves to help us understand. So they're not completely 100% true. So we have all those exceptions that fall into place, but they're helpful for us understanding. And so one of the things I said about valence bond theory is that it works really well for organic compounds. It works well for carbon, it works well for nitrogen, works well for oxygen, but the heavier elements, it doesn't always work really well for. And so that's not very satisfying to have a model that only works, what is that? 4% of the time. You know, we want it to work all the time. And so this is where molecular orbital theory comes in. It is much more robust. And so that's one of the advantages. Okay, so why is it more robust? Rather than saying, hey, let's change our orbitals into new orbitals, we're just going to work directly with the S, the P, the D, and the F orbitals. We're not going to make our atom decide, oh, suddenly I'm going to bond this way, so now I'm going to switch around and make these hybrid orbitals or those hybrid orbitals. So each atom retains the S, P, D, and F orbitals. Okay. And so this means that those orbitals have a particular shape and they have a particular direction that they point in. And the direction that they point in is going to be important for how molecules bond together. This also is going to do, is going to explain why some elements form dimers. So we have diatomic elements like hydrogen and oxygen, and others do not, like helium and beryllium. Just like with dot structures, it's going to explain multiple bonds. So all of our models do pretty well with multiple bonds, but it's going to do something that none of our other models have done thus far. It is going to explain to us why oxygen is paramagnetic. Okay. So what do we mean by paramagnetic? Paramagnetic, in short, means that we have unpaired electrons. So we have said thus far that electrons like to pair up. They can pair up in lone pairs, and they can pair up in bonds. But some atoms and some molecules and some compounds are paramagnetic. And what that means is that if I bring a magnet near it, it's also going to act like a magnet. It's going to be attracted to that magnet. And this can be observed with liquid oxygen, that if you run liquid oxygen through a magnet where you have, one of those U magnets that the ends kind of face each other, it's going to be attracted to that magnet. Whereas liquid nitrogen would not, and liquid helium would not. Well, you can't really get liquid helium, but other dimers would not. So we need an explanation for why that happens, and this helps us to do that. Okay, major disadvantage. If we have more than 2 atoms, this gets really complex, and we are not going to do more than 2 atoms in this course. Unfortunately, my juniors and seniors in my advanced inorganic chemistry class are not so lucky as you. They are about to embark on 3, 4, 5, 7 atoms and having to figure out these molecular orbitals for that. And none of them remember having discussed this as freshmen. So pray for them. Okay. So what do we know so far? We know that bonds get formed when orbitals overlap. We've talked about that with our valence bond theory. We've talked about that kind of in general with how are they sharing those electrons. They're getting close enough to each other that the orbitals can share. And that the better the overlap, the stronger the interaction is going to be. We're going to get better overlap if the orbitals are very similar in size or very similar in energy. So hydrogen has a really good, strong interaction with itself because they're both very small. But when I try to interact hydrogen with, say, iodine is so much bigger than hydrogen, the interaction is much weaker. So we want to have similar sizes and similar energies. All right, now this is the part where it gets a little bit confusing. In valence bond theory, we mix together atomic orbitals on one atom to form hybrid orbitals on that one atom. In this theory, we're going to take orbitals from 2 different atoms, an s orbital and an s orbital, and bring them together. So much like we talked with pi bonding, having that overlap of the parallel p orbitals, we're going to do that with all of these. It's always going to be atomic orbitals that are overlapping. There will be no hybrid orbitals involved. Now with valence bond theory, we said no matter how many orbitals we put into our mixture, we're going to get that same number out. So if I use 2 orbitals to make hybrids, I get 2 hybrid orbitals. We're going to have a similar pattern here. We're going to form from those two atomic orbitals, one on atom A and one on atom B, we're going to form a bonding orbital, and we're going to form an antibonding orbital. So we get two orbitals out if we put two orbitals in. The difference here is they are not identical. So one of them helps the atoms to stay together. We call that bonding. And one of them pushes the atoms apart, and we call that antibonding. And it's often designated with a little asterisk or star. And it is higher energy, which means when we are drawing a diagram, we put the bonding one on the bottom and the antibonding one on the top. And since we fill our orbitals from the bottom up, we fill bonding before anti. So we'll get back to that. So our notation in molecular orbital theory is a little bit different than it is in others. We would say, instead of calling it a sigma bond, we might say it has A symmetry or B symmetry or T symmetry or E symmetry. But since we're only looking at diatomics, those parallel pretty well with sigma and pi bonds. So rather than throwing new notations out of you, we're just going to stick with sigma and pi. So s orbitals can only form sigma bonds. And if I have two s orbitals, one on one hydrogen, one on the next hydrogen, I'm going to get a sigma bond and I'm going to get a sigma antibond. So what we're going to do is we're going to look at our diagram that we make and count up all the electrons that are in bonding orbitals and all the electrons that are in anti-bonding orbitals, and we're going to determine the bond order. So remember, the bond order tells us, do we have a single bond, a double bond, that kind of thing. Our bond order will be 1/2 the bonding electrons minus the anti-bonding electrons. All right, so we got some rules. Now let's see how this is going to play out. So if I have p orbitals, they can interact end to end. They can overlap end to end. And if they overlap end to end, they can form this kind of thing. So that's a sigma bond. That's our hot dog. Okay. Now with s orbitals, the hot dog doesn't have these little tails on the end, but with a p orbital, they do. So this is a sigma bond, and this is more stable, lower in energy. It can also form an antibond. So an antibond is the reverse, where the bulk of the orbitals, the atomic orbitals, is on the outside. And so because of that, it doesn't help these two things to bond. Has a node in the middle. Remember, a node is a no-no zone. There's no electrons on a node. Okay. So that's sigma bonding. And then we've already talked about pi bonding, and this is where instead of pointing at each other, they're parallel. So your sigma bonding is now at the top. I'm sorry. Your sigma bonding is now at the top. Up here, and the pi bonding is down here. All right, so we've seen this. This is a pi bond, but we also get the situation that rather than overlapping together, they kind of push away from each other. Pushing away from each other, we have this node, this no-no zone. That's our antibond. All right. It says, I will give you the background. So let me do that now. Let me know if I didn't get enough to your table. All right, so what I'm going to have you do is I'm going to have you fill in the electrons on these. Remember that just like with atomic orbitals, we're going to use arrows. So we have on each line an up arrow or a down arrow or both, right? And each of those arrows is one electron, and we have rules. And so our rules say, outbow says fill from the bottom up. So we count how many electrons we have, and we start at the bottom, and we don't move up until to the next level until we have a certain level that's full. And then we have poly. Poly says that in each orbital we can have an up and a down, and then we got to move on. Okay, 2 electrons per orbital. They have to have different spins. All right, and then Hun says if I get to a situation where I have degenerate orbitals, degenerate, remember that's one of your vocabulary words, they're the same energy level. So like all 3 p orbitals are degenerate. Then I spread them out as much as I can, right? I don't pair them until I have enough electrons that they have to pair. Okay, so how do we do an MO diagram? Each side represents one of the 2 atoms we're going to look at. We're only going to look at dimers, so we're not going to look at anything more than 2 atoms. So you can just write the symbol for the element on each side, and you already know how to count valence electrons. So you would figure out, okay, oxygen has 6 valence electrons, so I need 6 arrows on that side. Only show the valence shell. And then in the middle, we're going to show the overlap. So the overlap orbitals are shown for you. The way that we fill them is just to count up everything on both sides. So if I have 2 oxygens, that's 6 plus 6 is 12. And I use the same rules to fill in the middle that I did on the sides. Start at the bottom, 2 electrons per orbital, and then spread them out if I have degenerate orbitals. Okay. And then we'll look at bonding versus anti-bonding in just a minute here. Okay, so this is our first example. We're going to look at a homonuclear diatomic. So homonuclear means the nucleus is the same, which means it's the same element. Okay, so I have fluorine and fluorine. That's listed at the top. Now I've shown on this one the core electrons because if we were doing the atomic diagram, we would have those core, but we don't use the core electrons in bonding. So they're just kind of sitting there on their own. Okay. There are 7 valence electrons for each fluorine. So if I ignore that first level, you'll see 7 arrows on each side. Okay. So on your diagram, you are going to look at the very first box is fine for this. And so you can copy this into there, how it looks. Now, as we build the central diagram, we have the 2 s orbitals. One from the first fluorine, one from the second fluorine. They're going to combine and form a bonding orbital. That's the low one here. And an anti-bonding orbital. Okay, so the dotted line shows that these 2 orbitals are coming from this one, and we'll see another dotted line over there. My animation keeps getting messed up here. And then, whoa. I don't know what it is. Okay. One of the P's on each side can sigma bond. They can point at each other. Okay. And when they do, they're going to overlap really well. And so when they overlap really well, we're going to get a really stable orbital down here. So this is a sigma bond from the p orbitals. And a really unstable antibond. So the things on the top are the antibonds, the things on the bottom are the bonds. And then remember that our parallel p orbitals can either go up and down, or they can go in and out of the page. We have two sets, and they're equal in energy to each other. So we have two sets of bonding and two sets of antibond. Okay. So we use the sigma to designate the ones that are sigma overlap, and we use the pi to designate the ones that are pi overlap. And then I put where the orbital is coming from. So this is coming from the 2s, and this one's coming from the 2p. All right, and then remember the star means that it's antibonding. Okay, so now we have the diagram, and we're going to fill in the middle. How many electrons are we putting in the middle? So we need the valence electrons from each side. So if I were doing a dot structure, how many total valence electrons would I have? 14 total. So same thing here. So whatever number you would come up for a dot structure, that's what you put in the middle. So I'm going to fill those in from the bottom up. Two electrons on each line. Each line is an orbital. One of the electrons is up, one is down. That represents the spin. And it doesn't matter in this case, but if I didn't have to pair the ones in the pi section, I wouldn't pair them. I wouldn't have a pair and an empty orbital. I would spread them out. Okay, so in looking at this, I can determine a few different things. One of the things we talked about is the bond order. Okay, so for bond order, we're going to count our bonding electrons, and that's all of the ones in the orbitals that don't have strong charge. 2, 4, 6, 8 bonding electrons. Okay, then I count my anti-bonding electrons. 2, 4, 6. Okay. And then my formula is bond order is equal to 1/2 the bonding electrons minus the anti-bonding electrons. So it's going to be 1/2 8 minus 6. And what does that equal? 1. And if I were to draw the dot structure of the fluorine molecule, would I expect to find 1 bond? Yeah. So these two methods should complement each other. I should get the same answer whether I'm doing a dot structure or doing it this way. What this can tell us is how that molecule will change if I start adding or subtracting electrons. So if I subtract an electron from a bond, normally we would think, oh, if I'm taking away electrons, it's going to get weaker, right? But if I take away an electron from the fluorine, and so I have F2 plus, I'm taking away the topmost one, right? And that's antibond. Now I have fewer anti-bonding, and my overall bond structure gets stronger. I've got to stop stepping on these things. Okay, so I'm not going to worry too much about that right now, but just be aware that changing the number of electrons in a bond sometimes does weird things. That is best explained by molecular orbital theory. Okay, so we have discovered that the bond order was 1/2 bonding minus anti-bonding, and that was 1 in this case. We can look at, is it paramagnetic or not? So let's take a look back at the diagram. Are there any unpaired electrons in the middle? So when we ask these questions, we're just looking in the middle here. No. So we expect this to be the opposite of paramagnetic is diamagnetic. I don't know why it's not unparamagnetic, but it's diamagnetic. So this is diamagnetic. Okay, we also have some special names for orbitals. So the top set of orbitals where we have electrons is called the HOMO. That's the highest occupied molecular orbital. And the reason that's important is because if I gain or lose electrons, that's where it's going to be happening. I'm not going to really do stuff with the things that are down below. And then we can also talk about the character of any given orbital, but usually we talk about the character of the top orbital, the HOMO. And so we might say, is that a sigma orbital or is it a pi orbital? Is it bonding or is it anti-bonding? So I'll give you a chance to write this down and then we'll go take a look at that. All right, so if we're looking at the top orbitals here, we can say that the character of these orbitals is that they are what? Sigma or pi? Pi. So get a label right here that's pi. And are they bonding or anti-bonding? Anti-bonding because we have a little star. Okay. That's what we're going to do with this. All right. So I have handed out to you a paper that has some questions that you're going to do this with ions. Okay. So all we have to do with ions is just add in the extra electrons. I just walked right by you guys, didn't I? So I'd like you to take the next few minutes to work on that. I am going to pull up this on the screen and then I'm going to put you in one of the groups. You guys only have 2 people. Jordan will join your group. Provided he's still there. I don't know.
Something, boys.